Let's talk a bit here about accumulation of change and kind of how we add that up, and that's going to set the stage for integration, which is what this unit's all about. So if we're looking at area, what does that mean on a graph? So if a function describes a rate, the area represents the total change of whatever that rate is. So for example, for a velocity function, the area under that curve describes distance traveled. The area is always calculated between the y-axis, the function, and the x-axis. That's a mistake. That should be the x-axis, and so therefore the area below the x-axis is negative area. And you can use the geometry to find that area. So let's go to a quick example here. If this is time and this is velocity, and I have something like this, then this total area under the curve here would be the amount that the object moves. So this would, be 1/2 this final velocity times time would give us the area. If you had something like cars per minute, and then minutes here, and you had a curve like this, the area would tell you the total number of cars that passed. If you had something like kilometers per hour and you have hours, the area would tell you how many total kilometers have changed. So the idea here is if we're thinking about that our graph is a derivative, then the area would tell you kind of the original function, however much that original function has changed. So here's going to be an example, and pardon the inches, it's just because it was one that was already ready. A snowstorm lasts 18 hours. The graph below shows the rate of snowfall. So you'll notice we have a graph of a rate, and then they're asking what's the total snowfall. Well, if we have the rate of snowfall, the area under that graph will tell you whatever it's a rate of, in this case, snowfall. So if I just find the area of this graph under this curve, so between the x-axis and the function, that will tell me how much total snow we have. And this makes sense if you look at just, for example, this section right here. Well, if it's 1 inch per hour for a total of 10 hours, 1 inch per hour, and that's the rate, that's just the height, times 10 hours, it's easy to see how that would mean 10 inches total fell. Because, again, it's 10 inches wide and 1 inch per hour tall, so the area is, like we said, 10 inches, the total amount that fell. So by using kind of that same logic, in this first section, we see 2 hours times 1 inch per hour divided by 2, so that's going to be 1 inch. In here, this is going to be 0.5 plus 1 divided by 2, so that's 0.75, because it's the area of a trapezoid. 0.75 times 2 would give us, this will be easier if I just think, 1.5 times 2, so that'll be 3 inches. This area right here is 2 times 0.5, so that's 1 inch. And this area right here is 2 times 0.5 divided by 2, so that would be 0.5 inches. So we add all that up, 1 plus 10 plus 3 is 14, 15, 15.5 inches. So again, if you have a graph of a rate, and you find the area under the curve of that rate, that will tell you the total amount of change, or whatever the total thing that the rate was a rate of. So we'll look at a couple of other ideas in some more units to come.